Good evening. Am I audible? I'm going to share my screen now. Please let me know if it's visible. Is the presentation visible to all? Thank you, Kiran. So, should I wait for another 2 minutes before I start the class? Hope you all finished your assignment and submitted it on time. So, all right. So, I welcome you all to another week of live interaction session. This is our sixth week for the course Bioinformatics, Algorithms and Applications. So I'm Lavanya N. I'm a research scholar at IIT Madras in Protein Biophysics Lab. So I'll be doing the Friday sessions between 6 to 8 p.m. So let's start with the topics for week 6. The practice questions will be based on this lectures titled Protein Tertiary Structure 1 and 2 and Protein Structure Analysis Part 1, 2 and 3. So let's start with the first question. Which residue is most likely to be present on the surface of a protein? We can always use the chat box. Option A, valine. Option B, leucine. Option C, isoleucine. And option D, arginine. Devangana has answered. Any other answers? Thank you, Kiran. Sorry. I think my pen is not working today. All right. Maybe now it will. Yes. So I think the answer popped up a couple of times. But in case if there's anybody else who joined just now, okay, three people have answered D. What about these other options? just fix this. So the other amino acids are residues are more hydrophobic in nature than arginine, which is positively charged, right? So it's between polar and non-polar, and the likelihood of them being on surface is more for arginine compared to valine, leucine, or isoleucine, right? So I have a bar plot here where you have the propensity at surface and buried area. So for surface you have blue and buried is shown in red. So if you look at the residues that we are interested in, isoleucine, leucine, valine, and you have arginine here, right? In these three cases you see that the red ones are peaking, which means the propensity for them to be buried is much higher than. So buried is shown in red and surface is shown in blue. So this has a more propensity to be on the surface than these residues, right? So the answer is okay for Venkatesh, who wants me to start from the beginning. So Venkatesh, you're right on. I mean, you're lucky that you're still in first question. So we just began with the announcement of topics which you already are aware of. And this is the first question: which residue is most likely to be present on the surface of a protein? And amongst the four options given, three of them are aliphatic amino acids, right? And these are hydrophobic in nature with no polar residues or functional groups or positively or negatively charged groups present. Whereas arginine is positively charged and therefore can interact better with solvent molecules, right? Can tolerate more. Therefore, arginine has a greater propensity to be present on the surface, which is further shown here. And this is taken from a research article, and I've pasted the DOI here in case you want to check this out. So they've made a nice work on uh, going over the propensities of each amino acid residue, whether it's in the surface or buried, amongst all the PDB structures available at that time, I guess. So you can look into this. But pictorially, it's a nice way to see how residues get distributed in a protein structure. See, all the uh, polar residues have more height when it comes to the blue bar, and the non-polar residues have a bigger red bar. There are some residues which are kind of neutral, and it depends on the pH of the surroundings and where they are placed in order to be either surface or buried residue. So that was option D for question 1. Question 2: which among the following is the highest resolution in protein 3D structure determination? A 1 angstrom, B 1.5 angstrom, C 2 angstrom, and D 3 angstrom. Which among the following is the highest resolution? Thank you, GDCK. I don't know how I should call you. Hari. Okay. Thanks, Hari. Other answers? So when it comes to highest, I guess it's going to be a hard day today with eraser not being available easily. So amongst these values, which is the lowest? 1 angstrom, right? Although it's very very hard to get a resolution that good. But if the question asks for the highest resolution in protein 3D structure determination, then it has to be 1 angstrom and not the other options, right? Okay. Question 3. Which is not a protein visualization software? Option A, Pymol, B, Rasmol, C, Chimera, and D, PDB. Thank you, Hari. Others? Thank you, Malini. Thank you, Filza. So Pymol is a visualization software, so is Rasmol and Chimera, right? The only uh, option which is not a visualization software but rather a database is PDP. Thank you, Venkatesh. So all of you are right. It is option D. Question 4. Which is the first method to determine the accessible surface area? Is it access, DSSP, get area, or ASC? Thank you, Devamana. Any other answers? Very good guess. Gate area is kind of newer and comparatively not as old as the others. So there's one option out for you. The first method was access. Right. Question 5. Buriedness provides the information on the preference of residues in the option A, surface of the protein, B, interior of the protein, C, center of mass of a protein, and D, all of the above. Thank you, Hari. Malini, Devangana, 3 votes for option B. Others? Thank you, Filza. Alright, so buriedness obviously shouldn't give you any information about what is happening in the surface of the protein. And definitely, we are not worried about the center of mass of a protein when you're talking about the buriedness, right? And so it's not all of the above either. So undoubtedly, it is option B. Question 6. The databases containing information on structural class is Protherm DB and PDB, Cath and Pronab, SCOP and DALI, SCOP and Cath. Okay, 4 Ds popping up. I guess it's a straightforward question, right? So we know this is class, architecture, topology, and here you have structural classification of. So obviously it is these two which fit the question, but I thought I'll also include what the other guys are. Cath and scope are again covered. PDB, you know what it is. So I have a small area where you have protherm. Thank you, Venkatesh. So protherm is a thermodynamic database for proteins and mutants, and it contains data of several thermodynamic parameters such as melting temperature, free energy, denaturation, enthalpy change, thermal denaturation, sorry, and other denaturant, denaturation, heat capacity. Such data you can get from Protherm, And DALI is a protein structure comparison server. We might probably look into it in further classes where we will be comparing 3D structures. And this is the link for DALI. And ProNab is a database for binding affinities of protein nucleic acid. It's binding, I guess, and nucleic acid protein, P for protein, complexes and their mutants. So ProNab and ProTherm DB are developed by Dr. Gromiha's lab, I guess. So those were about these three servers, databases, right? So the correct answer is, of course, scope and gap, as you all said. Question 7. What is the probe radius generally used for a solvent molecule? Water. Assuming it is water, what will be the radius generally used? Thank you, Filza. Malini and Devangana Venkatesh. 4 votes. Others? Thank you, Hari. So all takers for option B, which is also the right one. So there are several pictures in the internet which you can look at, but I think I just got a text data here. Typically, value of 1.4 angstrom is which approximates the radius of water molecule is taken. Another factor that affects the result in definition of van der Waal radii of the atoms, the molecule in the study. So here, when you have water molecule, it's almost 1.4 angstrom, which kind of, you can take it as a sphere of 1.4 angstrom, but it's somewhere around 1.5 odd, I guess. So the right answer is 1.4, which is used for all practical calculations. So the surface area that you use for the probe determines what is the accessible surface area that you get in the end. So smaller the molecule, smaller the radius, greater is the more area that it is going to roll over, and greater is the accessible surface area that you are going to calculate for the protein surface as such. Who obtained the Nobel Prize for solving the structure of a globular protein? Was it Kendrew and Perutz? Option B, Watson and Crick. Option C, Venki Ramakrishnan, Tom Stites, and Ada Yonath. Option D, Dyson-Hoffer, Michael and Michel and Huber. So you can either know an answer for this question, no Googling, or you can take a random guess. Thank you, Filza. That was nice. So, thank you, Devangana. You can all take a guess. There's no harm in being wrong. What about B and C? It's all right. There's no harm in being wrong. You cannot always remember who solved what and when and did they get a Nobel Prize. But I can assure you that all these options are Nobel laureates. It's just who did what. More guesses? Okay. I don't think anybody would choose option B because now I think it's ingrained in all of us that Watson crick, Watson crick, Watson crick everywhere. So you know that the DNA structure was they got the Nobel Prize for the alpha helical model for DNA. So not these guys definitely. So your hopping will be between A, C, and D is what I thought. Therefore, I made few pop-ups for A, C, and D, and not for B. Right? So, Nobel Prize in Chemistry 1962 was for Max Perutz and John Kendrew for globular protein, and it was hemoglobin. Watson and Crick already discussed. To the right, you can see Nobel Prize in Chemistry 1988. What's that's 26 years later, right? Was awarded to Dysenhofer, Huber, and Michel for determination of 3D structure of photosynthetic reaction center, which is kind of on the membrane, right? As Devangana pointed out, and Venki Ramakrishnan, Tom States, and Ada Yonath in 2009 was awarded for studies of structure and function of ribosome. Cool. So the answer is A. We can move on. Question 9. Which software provides ASA values in pictorial form? Option A Axis, option B DALI, option C PDB Sum, option D ASA View. Thank you, Venkatesh and Malini and Hari. 3 votes for ASA View. And Phil's also agrees. No question here, right? ASA View gives a pictorial representation of accessible surface area. We have the same picture that was shown in the lectures, I believe, and this is the DOI of Dr. Bromiha's paper on this. Question 10. What is the surrounding hydrophobicity of threonine 27 if it is surrounded by 2 alanines, 1 valine, 2 threonines, 2 glutamines, and 1 serine? The hydrophobicity values are ACGMY, FILBW, DEKHR, NPQSP. I don't know why it's not erasing the other one, but this is 1, this is 2, this is -2, -1. And you have 3 on in here. 27. Thank you, Devangana. Let others come up with their own answers. So you have two alanines, one valine, two threonines, two glutamine, and one serine. I wrote it full, but I'm not going to bother getting an eraser again. So, how should you calculate the hydrophobicity values? Right? So, summation of how many do you have? 1 into valine. So, valine is here 2 plus, since I'm using plus everywhere, I don't think I need to put summation. So, this is done, followed by 2 into threonine. Threonine is T minus 1 plus 2 into glutamate, that would be E, right? 2 into minus 2 plus 1 into serine, that will be S, which is again minus 1, plus 2 into alanine. Alanine is A, which is 1. So to summate, 1 into 2 is 2, 2 into minus 1 is minus 2, minus 2 2s are 4, minus 1 plus 2. 2 and 2 go away, minus 5 plus 2 minus 3. So that Devangana is right. Anybody else getting any other answer? No? Is everybody clear with this? I can move on, right? Okay. I'm going to take that as an yes and choose option B as the answer. So we'll go into the current year's assignment. An atom with a temperature factor of more than 75 shows that it is option A rigid, option B flexible, option C located in a fixed position, and D none of the above. Thank you, Devangana, Filza, and Hari. Athilita and Venkatesh. So 1, 2, 3, 4, 5. Right? So whenever the B factor or temperature factor is greater than 50, it means they are flexible. And less than 10, they are kind of rigid, or you could call them fairly stable or not moving so much. Right? So instead of Rigid, I'm going to go with fairly rigid. So 75 is greater than 50, therefore I'm going to go with flexible. It's definitely not rigid. And located in a fixed position is the synonym of rigid, so it doesn't go with this and not none of the above. The right answer is B. Question 12. The solvent accessibilities of residues alanine 7, glutamine 8, glutamic acid is 8, valine is 9, and aspartic acid is 10. And alanine 11 in a protein. I'm sorry. Alanine 7, 8, 9, 10, 11. So all consecutive residues, alanine, glutamate, valine, aspartate, and alanine in a protein are 0.256, 1.2, 25, and 78 angstroms squared. Residues located at the interior are. Okay, three have answered. Good. Venkatesh, Filza, and Hari. So, whenever you are talking about, let's say this is the surface and this is towards the interior. This is just a random representation, need not be factually true. So, when we have a protein structure like this, the green residues are more accessible to the solvent and putting the solvent molecules as smaller dots or dashes, whereas the circles are residues compared to the dark blue ones in the center, which is away from the surface, more buried, right? So, residues located in the interior will have lower solvent accessible surface area than the ones that are exposed. So look at this order: one, two, three, four, five. I have this as A, B, C, D, E. Then I should go with A less than C, less than D, less than B, less than E. Right? So the combination given here are 7 and 9. So A is 7, B is 8, C is 9, D is 10, E is 11. So this seems like a reasonable answer to me. 8 and 11 are the most exposed, therefore this is wrong. 9 and 10, okay, but when you have 7 and 9, this is not the best option. 7, 9, and 10. 7, 9, and 10, again, you have three options which are falling on the leftmost side of buriedness. But when you take option D, just 25, right? But when you're looking at point 0.2 and 1.2 and 25, it's already an order of by, I mean, 10 times or 20 times more, right? Here you would say it is 100 times more if you compare it with A, and comparing it with C, it is already 20 times more. So for interior, I would go with option A and not C or D. Definitely not B, right? Question 13. A protein has 25 valence, and among them, 5 are on the surface. The transfer free energy of valence is, where gas constant is 1.987 calories per mole per Kelvin and temperature is 300 Kelvin. Is there a maximum or minimum? So you can go with buriedness factor, like how we saw here. Uh, there is no set number for like B factor, but here it depends on the, how would you say, the surface area of the protein also, right? Some of them might be really extended. Each protein is unique in its architecture, so what you might consider as buried for one protein may differ from what you consider as buried for some other protein, right? So you cannot go with a particular although you can set thresholds, that's fine, but with just surface area. This is for the previous question, by the way. I shouldn't pollute this slide. This is for the question that Devangana asked in the chat. And as for a surface area alone, you cannot say that it is exposed or buried. If you divide it by its extended surface area, then you can. Like percentage accessibility, yes. But with just accessible surface area, you should not go with it. Okay, Filza has started answering. So has Hari. How come? Okay, two votes for A and one vote for B. Now this is interesting. Others, what's that sound? Did you guys do something? Any raise hands raised and or questions asked? Okay, I mean we will definitely look into this. I thought I heard some notification. All right, we'll go continue. How to calculate this first? What is the formula for calculating? Where's the full screen mode? Oops. So how do you calculate transfer free energy? Is given by minus RT ln f of I, right? And what is f of I? Which is the ratio of number of residues in the interior by number of residues in the exterior. Okay, so you're starting with the ratio of residues distributed in the interior of the protein to the exterior of the protein. So how would you decide what is interior and what is exterior? Just like what Devangana asked, you have to go with how much they are accessible to a surface area, have a threshold, which is depends on the protein that you're looking at, depends on what the user wants. So and also on the percentage accessibility, and then you set a value, right? Because some residues are more bigger than the others. Now in the question you have said that there's a total of 25, right? And among them, 5 are on the surface. So in 25, if 5 are on surface, then 20 should be on or should be buried, right? So surface would be exterior, buried will be the interior count, and I here is Valen. So f of Valen would be number of interior is 20 divided by number of exterior is 5. 5 fours are 20. So what does that give you? Is equal to minus RT ln 4. So that is minus 1.987 calories per mole Kelvin into temperature is 300 Kelvin, right, into ln of 4. So I'm going to use my calculator. Ln 4 is equal to 1.386 into 300 into 1.987. So I'm getting minus 826.37 calories per mole. Is this what you're all getting? This is a little badly written. So it's 0.37. I'm just waiting for you all to say yes or no. Okay, Venkatesh also says yeah. I mean, Amreen, sorry. Amreen, I hope Amreen understood how this is being done. Okay, Rohini, we'll look into this. Exactly, Devangana. So when you look at this and jump to this, your most favorite option will be A, and all the others look absurd. First of all, we got our answer in negative, therefore you can omit C and D. What's the difference between A and B? Look at the values here. There is no kilo, right? But you have a big case sitting here. So that is the reason A gets discarded. So when you look into the units, everywhere it is in kilocalories. So if I express it in kilocalories, it will be minus 0.82637. So that is 8264 or 826. So if I uh, take significant digits, happy Rohini, so it's 0.83 kilocalories per mole. So your option should be B. So I think Devangana got it right. Good question. So let's go on to question 14. In homology modeling, SCR stands for option A structurally conserved regions, option B structurally catalytic regions, option C is sequence conserved regions, and D semi conserved regions. Okay, three A's popping up: Hari, Devangana, and Filza. Fourth one by Priyanka, fifth by Venkatesh. Any other A's? Any other options? Madhulita also joins. Okay. So we all agree that it is structurally conserved regions. Cool. Okay. Question 15. From the given contact map, which of the following pair of residues form a short range contact? Option A, isoleucine and glutamine at 4 and 8th position, leucine 2 and arginine 6 and isoleucine 7, serine 10 and leucine 2. A, B, C, D. Drop in your answers. Wait. Of course, Hari will be looking into the explanation. Contact maps are visual representations when you know that two residues are interacting, right? Whenever there is a contact between uh, two residues, you put a dot there. If not, you just leave it blank. Now you see that leucine in position 2 is interacting with, of course, itself. So that's why I put a dash over the diagonal residues, because obviously it is going to be in touch. This is null. You can either have it as dots or have it as blanks also. And it is interacting with arginine 6, glutamate 8, and serine 10. Okay, so you're having dots there. And look at this, it's in position 2 and it's interacting with residues 4 places away, 6 places away, and 8 places away. Okay, so it is having long range interactions with multiple residues. So we call something as short range when it is closer to the diagonal. It's symmetric on either side, right? Whatever you have, 1 2 3, 1 2 3 4 is same here too, right? 1 2 3. And just putting shapes so that you recognize that they are the same, symmetric in both sides. A little farther, some, in this case 4 to 6 residues would be medium range contacts, and even further will be, see, now 2 is interacting with 10 here. It's the same thing. This is a long range interaction. These could be, you can call medium. And here you have short range contacts. So what is this short range contact? It's between fourth and fifth. So sequentially also they are close, same as 4 and 5 here. They are close by. Similarly, here you can see 6 interacting with 7. Same is the case with 6 interacting with 7. They are close together. Whereas when you see 2 with 6, arginine is here, leucine is here. They have so many residues in between. We are talking strictly sequentially here, right? Structurally they are close by, that's why you have a contact in the first place. These are contacting with this are contacting with this, but in the interim you have so many loops and sheets or helices going on, and therefore you have multiple residues on these places, right? And again you have one more case here where 9 and 10 interact. Sorry about the crossness of lines, but I guess you get understand the point by now, right? So now look into the options. So short range contacts, what are the candidates? 4 and 5, 6 and 7, 9 and 10. Now look at the options given here. 4 and 8. First check whether they even interact. Yes, 4 and 8 there is an interaction. Let me change the color. God. hard day today. Options in color, something like this. So this is your first option. This is A. Okay. Same is the case with 4 and 8. Option B is 2 and 6. Where is that? 2 and 6. This is your option B. Okay. And 6 and 7 is option C. 10 and 2. This is option E. So I immediately told you that 10 and 2 is a long range contact. You can see, you can either go from the, how far is it from the diagonal? And look at this. So D is the longest, farthest away, right? So 2 and 10 cannot be your option. The other two, 4 and 8, 2 and 6. 4 and 8 and 2 and 6 are kind of similarly distanced from, because there's 4 residues here and another 4 residues here, right? So both I'm going to call them as medium range contact. So that leaves you with only 6 and 7. Again, only 6 and 7 are there in this pair of pairs of possible short range options that you can choose. So there's no 9 and 10, there's no 4 and 5. But 6 and 7 is present, which is C, and which is indeed short range. So was that convincing? Amreen and Hari? Okay, so there goes your answer. C. Question 16. The accessibility of residue arginine 74 in the extended and folded states are 165 and 90 angstrom square. The percentage of accessibility is dash percent. Thank you, Hari and Debangana. Others, please work it out. Or if you remember from your assignment, what is the percentage accessibility? Since my eraser is also bad. Hmm. So how do you write? Just the others. I'm waiting for you. Surface area in folded state divided by, thank you Rohini, surface area, and we are talking about accessible in extended state. So what is the area ASA found in folded state divided by what is the maximum possible ASA in a extended state? So extended and folded is 90 Armstrong square divided by 165 Armstrong square. Should be here ideally, but I'm not going to bother touching the eraser now. Okay, is equal to, or I could do one more thing. What is 90 by 165? 0.5454. So 54.54 percentage, as all of you have. Of course, you can drop the 4, it doesn't matter. Falls within the range, therefore, we are right. Okay, question 17. Number of available structures in PDB is approximately option A 10,000, B 75,000, C 1.9 million, and D 1 million. Thank you, Hari. A very straightforward question. All of us know what the answer is. Okay, nobody else. Thank you, Priyanka. It's option C. It's actually close to 2 million now, but this is the closest option that we have. Thank you, Madalita. So, question 18. What is the cutoff distance for identifying aromatic sulfur interactions? Okay, Hari says B. So does Debangana and Priyanka. 3 votes for B. But I guess this is already solved for you, right? So, no point in giving votes. Any other answers, or shall we move on? Look at the options. 10 angstrom is really far, right? For aromatic sulfur interactions to happen. So is 8. So an ideal distance would be somewhere around 5 to 7 angstrom. And the only option that falls in that range is B. Not D is too close, and C and A are too far apart. Right, so for this case, I quoted a research article. This is the title of the paper: Models of Sulfur Pi Interactions in Protein Structures. Okay, so after optimizing several initial configurations, they report that the optimum configuration has an interfragment separation distance from sulfur to center of the benzene ring, okay, of 4.4 angstrom, an angle between the planes of 56 degrees. And this was for using a benzene ring where it was placed right above the structures. So this is a very lower estimate of distance, which is not practical in a protein scenario. But they have other references, so I thought I'll post this work here. And while you search for other research articles also, they keep 5 angstrom or 5.5 angstrom as the cutoff distance for identifying aromatic sulfur interactions. I mistook this article. There is one more where an exact of 5 or 5.5 is given. So either you can look into that, or I can post it here while uploading the PPT. Alright, question 19. Proteins containing alternate alpha helices. Yes, Rohini. I also found certain articles that said less than 6 or less than 7. Okay, and less 7 was a very higher upper limit. So less than 6 angstrom, but it should be somewhere greater than 4 or 5 angstrom. So between that range. Proteins containing alternate alpha helices and beta strands, which are segregated from each other, belong to all alpha, all beta, alpha plus beta. Okay. Thank you, Hari and Priyanka. And Delomera, Madhulita. So, has anybody unmuted themselves? Somebody speaking? Okay. Getting back to the PPT. So, I think we're all agreeing on option C. So, when you're talking about, oopsie, alpha helices and beta strands, there goes your all alpha and all beta, right? So the competition is between, are they plus or bi. So you call something alpha plus beta when you have both alpha helices and beta strands. Maybe here, here. I'm just randomly putting together things, so don't think they are actually directional. Alright, it's a very random thing. So when you have both alpha helices and beta strands, they're going to wind around each other. That's not a point. But in alpha plus beta, you're going to have stretches of alpha helices and stretches of beta strands, beta sheets, followed by stretches of alpha. I think I have a picture slide put up for this. Okay, this was somebody's online slides which I used for this class. Now look at alpha plus beta and alpha by beta. Now when you look at the protein structures also, there is a little segregation between the alphas and betas, but not so much. When you compare, I mean, I could argue that these also have some stretches of alpha here, some beta, and then some alpha and beta. All right. So you cannot always say that the alpha helices bundle up towards one end of the protein and the beta sheets bundle up in the other sides of the protein. But look into the, so these are PTI, LZM, and TLS are three things here. Okay. Now look at where their structures are and how the sequence is shaped. The stretch of alpha helices here are these blue balls in this end, and between that you have beta strands. And can you see the single ball? That's this alpha. I think I should use a different color simply because there's blue and orange already here, so I don't want to. Okay, I'm going to go with green because green is nowhere here. So this alpha, all right, that's here. Okay, but when you see in the sequence, there's a stretch of alphas and beta, so they are segregated. But in this case, you have alpha helices and beta strands that alternate. Don't think these are individual residues. These are stretches of secondary structures. Okay. So immediately you have alpha, beta sandwiching each other. So there's always crossover between this, that, this, these, those. So you can look at the structures. These are more um, all over the place, right? And the sheets are mainly parallel due to beta alpha beta folding units. But the beta sheets here are mainly anti-parallel due to the beta beta hairpin folding. So when you have one beta close to the next one, this will be the anti-parallel beta beta hairpin thing, right? But if you're having one thing followed by another helix, it gives you an opportunity to form another. This helix need not be in the same plane, it could be above, below, anywhere, right? Something like that. Well, it's hard to glean the very first time when you look at protein structures or trying to understand while you're just starting, okay? But as you look into more structures and understand structural organization better, you will be able to recognize alpha beta or alpha plus beta and alpha by beta, right? But for the purpose of this question, containing alternate alpha helices and beta strands which are segregated, that's your clue, from each other belonging to alternate. Yeah, those are the problems here. If you just talk about alternating alpha and beta, immediately you will jump into it's alpha by beta. But then this is also alternating, right? You're having alternating alpha helices and beta strands segregated from each other. So that's where when this comes in, it takes precedence over alternating, because anyway you have both alpha and beta. So and there's nothing else. Only if you have A, B, and C, you can say they are not alternating or mixed something else. But if you have A and B and both of them are going to exist, so at some point you're going to have A's, B's, A's, B's, A's, right? So don't fall for alternating. Look into whether they are segregated or mixed, interspersed, or however they're going to word your question. Okay. Question 20. If the atoms of a particular residue have an occupancy of less than 1, it implies that option A, the residue is solid. I'm sorry, the residue is said to assume alternate conformations. The residue is missing in some cases. The residue is flexible. And D, the residue is not conserved. Okay, Devangana and Hari say 1. So whenever occupancy is equal to 1, it means that all conformations of the protein have this particular residue in the same position. Position or orientation, right? So conformation, when does conformation come? When you are having alternate uh, structure. How do we say? So proteins are dynamic, right? They're not very rigid molecules. So your side chain molecules can always flex. The antibiotic also, when you're capturing the structure in a solution by NMR or when there is a binding molecule, or even if you take a crystal, all protein molecules within the crystal are not going to be in the same orientation or exact uh, same structure, right? There are going to be slight variation in only in angstroms or tiny degrees. Or the whole structure is not going to vary so much, but you might have slight differences in how each atom is oriented in a particular structure. It just means that those regions where there is some deviation between multiple protein molecules, it means that, let's say this is a region and you have a lot of conformations arising out of differences in position of residues in this region. It means it is more flexible compared to the other regions which are almost having the same shape, orientation, position in all 10 conformations same. Okay, so it's not about missing. The residue is flexible, true. The residue is not conserved. Again, we are not talking about being conserved or not. The residue is said to assume alternate conformations, right? If the atom of a particular residue has an occupancy less than 1, when you're talking about occupancy, you're looking at, is this how my protein or this atom is in all structures, or is it distributed? Is it 30% in one mode, 60% in something else? Is it 45% in one and 55 in something else? Or is it 100%, which is one, or 90 and 10? So you're talking about how it is distributed, how this conformation is, or how the atoms are distributed in different conformations. Or is it zero point 0.3, zero point 0.3, and 0.35 and 0.35? Right? How many conformations does it sample? So the information that you are looking at from occupancy is not whether it is flexible or not. You have other parameters for that, right? That's what temperature factor is doing, whether it is flexible or rigid or other stuff. But from occupancy, the information that you are trying to gain is the presence of alternate positions, conformations, or alternate possibilities for that particular protein, whatever molecule residue the residue belongs to, right? So option A is the most appropriate or correct answer. Okay, so with this questions for this weekend, I thought of making an exercise while we do, I mean, if we have time, which we have in abundance. So in case you're all bored and ready to spend a little more time, we could find the actual number of, mm, so what's the number of structures from PDB as of today? So where should you look for people who didn't know where to look at the, yeah, I think my pen won't work here. So 2 million, right? Or if you go by Indian metric system, 2 lakh 2,292 structures from PDB. So I thought I will also look for something. Okay, so let's go with myosin. So actin and myosin, right? So we get a lot of structures from papain. All right. So look into this. You have 3,103 structures here. So now, if I were to give Homo sapiens, and I'm not going to go into eukaryote type of, and let's choose Okay, let's see electron microscopy, right? For X-ray diffraction, it goes as low as 1.5 to 3 angstrom, I think, and NMR will give you little above that only, which means it's not as sharper. But of course, NMR is not technically you cannot talk about sharpness there. It's more of how the residuals are moving, dispersion, everything. So, but let's look into electron microscopy because it's more interesting. Of course, we're going to go for protein. I'm going to go for say 2 to 2.5 angstrom. So now remember 3103 structures. So Ambreen, I just typed PDB and RCSB org. Yeah, you can just go to PDB and then I typed myosin here. You can type any random protein. Okay, so this is a structure. We can go into this and probe, but that has already been shown in your lectures as well as the PDB demo. So I thought I will look into this, and I'm looking into it right now when I'm doing this. So if you click on this count, you can see this 3103 displayed here. Now I'm going to click search after refining the results. So here you have structural attributes. So I'm going to choose molecular features. Okay. Uh, yeah, we could go with, let's go with myosin head. Okay, so you're looking for the exact phrase in the entity description, whatever title is here. When you have 3103 structures, you will not be able to choose, right? If you're looking for something specific, you can use all these advanced search options. I'm going to add another attribute, and this is an and. So, which means it has to be this and that. So, in methods, I'm going to go to experimental method, and here I'm going to choose electron microscopy. All right. Now I'm going to click on count again. Oh, there are just two. Here, okay. I'm going to click search again. Now it says no results matching the current query were found in PDB because of this guy. Because myosin head made it very specific that only two structures were available. So now if I press enter again, you're getting 93 structures. So this is a refinement from 3103. Now I'm going to do one thing. I'm going to go back to X-ray diffraction. Instead of myosin, I'm going to again go for myosin head. Now I'm going to count, just two again. Okay, let's see what happens. So both are by X-ray crystallography. So 1 to 2 of two structures. Nucleotide free scallop myosin near rigor state. Scallop myosin complete complexed with something. Okay, so you're having 4.2 angstrom resolution in both cases, and these are deposited by the same authors, probably for the same paper, right? And we got this because it is listed as myosin head here. Okay, now let's do something else. I'm going to change. Let's do green fluorescence protein. I got that because it said here, right? Example type green fluorescence protein. So now I'm tempted. It's one of the beautiful or standard beta barrel example that people give. So here I'm going to put So I'm just randomly getting. So the count is somewhere near 2 million, but there are just 6 here. So let's search. So similarly, you can also, okay, these are GFP like proteins. If I remove this, okay, I remove this and search, it is giving you somewhere around 17 million. So let's take a quick look at how this views 3D view. So you can see the barrel like shape here, right? Of course, in the ends, you have few helices. It's a very nice, beautiful structure. You can zoom in, zoom out, orient, and again, like eyeball, you can remove water. When I click this, it's hidden. Again, I click it, I can see, right? And if I click on this, you can see there's a molecule in the middle. Okay, and if I remove that, if I click on this, it moves. So when I click on a molecule, all the interacting residues are shown. Can you see? And I think we will be um, doing all this in detail because I don't want to spoil it before. Ha. So now you see it is in a different color. So I just wanted to make it a little more viewable. Now I can hide or show this molecule. So what are these guys? For information, this is just to view, and you have the sequence displayed here. So the polymer also it's shown in cartoon. I can change that as well in the three dots here. Add representation, ball and stick. It is adding and not uh, over the same structure, but it's not removing or changing the property. So by element index, I am coloring, which means according to the index, it is getting colored, starting from blue to red, I guess. You will get better representations with Pymon. Now you can also take a snapshot of this screenshot or take snapshot. You can orient in a particular direction. Now this ball and stick representation you can remove, and there you get the structure which you can take a snapshot of. So this was 3D view. Going to annotations, you can get all its connection between other homologous proteins. So the architecture is called beta barrel and mainly beta. You can even call it all beta or mainly beta. Now structure summary. So here you can find the total structure, weight, atom count, model residue count, and all that information, and you can click on this validation report. Okay, so when you get to this, it gives you all information: EFAM, CAT scope, chain wise. And here you see only one chain. This is again the 3D motif. There's somewhere where I used to get. So it says it's a monomer. And there's another related server where you can link where you can get more information on what molecules were used or what other polymers are present in the chain, and where you can find the data of or literature on those. I think I might have mixed things up. All right. So anyway, we saw some filtering methods in PDB. So with this, unless you have any other questions to ask for today, if you want me to repeat anything, any doubts, I think we can wrap it up. There wasn't much of a calculation today except for hydrophobicity, surrounding hydrophobicity, and this transfer free energy calculation. 11 and 12, sure, Kiran. So, apart from that, there's nothing else, right? Yeah. Going back to 11 and 12. So, question 11 is an atom with a temperature factor of more than 75. So, in PDB, okay, so in this download files, you get this PDB format. Uh, I am personally not using any textbooks. I'm going with the lectures. And there was a book that I used to refer to during my UG days. It was a book by N. Gautam, I think. Basics of Bioinformatics or something like that. I can put in a picture, but I would recommend that you follow the textbook that the course recommends for this particular course if you're very worried about doing this course. Otherwise, there are a lot of online resources these days. So many Coursera sources or newer versions of textbooks coming up. If you are focused on, if you want to score for this course, go with Sir's lectures and textbook. But in general, if you want to learn a lot, given that bioinformatics is itself about exploring learning in the lurch, you should look for textbooks online, look into the contents. If it helps you, great. I can put in the title of the textbook that I used to use, but again, it's more than 10, 20 years old. So by when it was written by the author, I mean. So it's going to contain almost the same information that Dr. Bromihas lectures have. See, even for that matter, you have AlphaFold now for predicting structures. I think that will be addressed in classes. Structure prediction will come in forthcoming weeks, right? But so if you look into the downloads, yeah. So you know where do you get the temperature atom or heteroatom is where the first column followed by the residue number followed by the name, and you have the residue name, three-letter code, followed by which chain it is in, so chain A, and then within that you might have the numbering based on how the author gave the numbering of residues. So this might be 1 according to the atom, but the residue name, so look here that first 7 atoms belong to the first residue, but the residue numbering according to this structure deposition is 111. There might be a full length version where the structure residue name starts from 1. Okay, so all 7 residues in this case belong to 7 atoms, I'm sorry, NC alpha COH Ha2 Ha3 belong to first residue, which is glycine here. And here you have XYZ coordinates followed by occupancy, which means all of them are in 1, and you have the temperature factor. I don't know why it is 0 in all cases. Maybe they did not deposit temperature factor. Let me look into some other structure. Mm, so this is an X-ray residue structure. So I'm going to download. I'm sorry. So open with notepad. So again, I'm going to go down to the. See here, you have the helix where it is, and so these are temperature factors, B factor 74, 68. So this is where the protein begins. So it is more exposed, whereas when you go further, it is 40, 39. Unfortunately, you are having aniso in between. So so you have a case of 70 here and 37 here, 34, 33, 32, 31, right? So the general threshold is that if a structure has a B factor above 50, it is more flexible or hard to pin. It will not be even barely seen, is what sir used, I guess. But if it is below that, it is not shifting so much. So this is 52, 55. So 70s are all very, very flexible. 47 almost there. But below that, they are showing a little more rigidity. So look into this one here, or I'm not seeing lower values to show you. 30s are what I get maximum, not 20 or. But of course, this is also small protein, not very. I see 131. That's it. 35s. So below 10 is very, very rigid, where they do not have any alternating conformations. So I guess this protein in general has multiple conformations. Now, if you look into the structure in pi mole as well, I think it's taking some time. So we will definitely be doing this in other classes. So this is an NMR structure. So if you play this, you can see it is having multiple conformations, right? Some of these atoms are, they look like they are kind of, what do you say, juggling, right? They are vibrating. So which means they are sampling multiple conformations. Here some 10 states are shown. If I look at them one by one, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can rotate and view all this. Of course, we'll be doing all this in forthcoming weeks. So to answer your question, when you have a structure with temperature factor of more than 75 shows that it is not rigid, because if it is rigid it will have very low values of 20 or 10. Okay, and so it is not rigid, therefore located in a fixed position is also wrong. So the only right answer is flexible, which is also true. So it's greater than 50, which is flexible. And question 12, the solvent accessibilities of residues alanine. Here what we had was, you're having five residues, and they have given you the accessible surface area, ASA of these five residues. Why am I unable to write? So what is it here now? We have ALA 7, U 8, Val 9, 10, and 11. And the values are zero point 0.2, 56, 1.2, 25, and 78, and all these are in angstrom square. So if a protein is like this and it is composed of residues all around it, it's a 3D structure, so these regions are all accessible. So here you might have a greater surface area exposed, here you might have less, but these are all exposed, so the accessibility is more. But think about a residue which is somewhere in the middle, in the interior. It is not going to be absolutely excluded from the solvent, but there will be a very minor crack of crevice surface for the solvents to go. And now you're talking about a probe of, if you're assuming water of 1.4 angstrom, to go and roll over this protein surface and tell you how much area is accessible. So when water molecules are able to roll over these surfaces and give the values of 78 angstrom square, 56 angstrom square, which means this glutamine in position 8. So this was glutamic acid, glutamate in position 8, and alanine in 11 are highly exposed. Aspartate, not so much. It's neither buried, not very, very exposed. But alanine 7 and valine 9, these are in the interior of the protein because zero point 0.2 Armstrong square. Can you imagine? That's the surface area. And 1.2 Armstrong square, that is absolutely, it's lower than the resolution of a protein structure. Do you understand? So these are very, very negligible small areas. So we rejected 8 and 11 for the reasons that they are exposed, and 9 and 10 because they are not. When you have 7 which is on the lower side, without 7, if 9 and 10 are present, it's not the best option. But with 7, when they are present, true that these are interior, and you have 7 and 9 alone. When given these two options, and considering that aspartate is 25 angstrom square and compared to zero point 0.2 and 1.2, this is very big, right? 20 times more if you're talking about Valen, and around 100 times more or 120 times more if you're talking about alanine. Therefore, we went for option A, where 7 and 9 residues are interior. Was that enough, Kiran? So, anything else, guys? If there are no more questions, we can close this session. Thank you, Rohini. Hope to see you all in next week's class. Same Friday, 6 to 8 p.m. All right, then. Have a good weekend, you all. Enjoy. Good night.